Okay, this is the first lesson, set theory and probability axioms. The material that we are going to study today is compiled from the textbook by Yates and Goodman. Okay, and third edition. So that's the textbook that we are going to follow, actually. And this slideshow refers to chapter 1. So you may need to have a look at chapter 1 and try to understand the concepts that you do not understand from this slideshow, or the concepts that are difficult to understand. Please refer to this textbook and chapter 1. The outline is simply applying set theory to probability, and then probability axioms, conditional probability, partitions, the law of total probability and Bayes theorem, and independence. Okay, we usually start with experiments in probability theory. An experiment has a procedure and observations, and there is always an ambiguity and uncertainty in the observation, and this is very widely used concept in we can talk about your questions later, okay? At the end of the lesson, I will ask questions. I will ask you if whether you have any question or not, and then we can talk about that later. Okay, in an experiment, we have procedure and observations, and it's widely used in probability theory. And there's always an uncertainty in the observation, so that we talk about probability. Here is a list of experiments. Here you see flip a coin, for example. The result is head or tail. Walk to a bus stop. So how long do we wait for the arrival of a bus, for example? We give a lecture, and how many students are seated in the fourth seat, for example, fourth row. This could be some examples of experiments. Now, in an experiment, we have an outcome. Outcome is one of the possible observation of an experiment. And sample space is the fine-grained, mutually exclusive, collectively exhaustive set of all possible outcomes of an experiment. Here, these terms are critical. Mutually exclusive, collectively exhaustive sets. So in here, as you see, comment 1.1, you see collectively exhaustive sets and mutually exclusive sets. If we have n sets, A1 to AN, if we look at the union of these sets, if it gives the sample space, then this collection of sets is called collectively exhaustive. Okay, collectively exhaustive. This means that this collection of sets forms the sample space. And mutually exclusive sets, where we have disjoint sets, actually, if there is no common element in two sets, then these sets are called disjoint or mutually exclusive. Okay, now from set algebra to probability, you can see the terms, how we use the terms in set algebra and probability. In set algebra, we use set. On probability, we use event. We have universal set in set algebra, while in probability we have sample space, and elements are the are the smallest components in a set, while outcomes are simply the observation of the experiment, so the elements of sample space. Okay, we start with examples. You will see in the slideshow that we give theory, some definitions, and then followed by many examples. Okay? Now, in example 1.1, which is quite popular, and we'll be using this example later in different topics. We have a Phone Smart. This is the name of the company, let's say. Offers customers two kinds of smartphones. Apricot. These are some, fake trademarks, just like Samsung, Apple, for example. Apricot and banana. It's possible to buy a banana phone with an optional external battery. So banana may come with external battery. Apricot customers can buy a phone with external battery or an external memory card. So Apricot customers may take an external battery or a memory card, or both. Draw a Venn diagram that shows the relationship among the items A, B, C, and E available to Phone Smart customers. So this is a typical set theory example. We have a sample space here. So here is my sample space, and there are basically two types of mobile phones. So we can divide the sample space into two simply. A refers to apricot, B refers to banana. Altogether, it forms the sample space. Now, in A, apricot, you see, we may have, for apricot, we may have either E or C. Okay, so E and C should be somehow the components of A, while for B, we have only E. So if I define an E, let's say this is E, then E is common to A and B, while C is only for A. Okay, so here is my C. Okay, so understanding of the experiment here is critical to draw this Venn diagram. Here is an experiment. So as we said earlier, experiment consists of procedure, observations, and a model. Here we have a Phone Smart company. We monitor activity in a company store and observe the type of the phone the customer purchases. And then we use a model. We say that probability of purchasing an apricot or a banana are equal. And the result of each purchase is unrelated to the results of previous purchase. So any customer might purchase an apricot, and the next customer might purchase apricot or banana. So they are unrelated to each other. So this is how we use set theory and experiment in probability. Here is an example again. So it's about example 1.2 again. So Phone Smart company, Phone Smart store. Here we have a sample space, as we said earlier. So we got a sample space here, A and B. So we can define a sample space here with elements A and B, where A is the outcome that the apricot solved, B is the outcome that banana solved. And if we talk about, for example, three customers, let's say, okay? 3 customers are coming into the store. let's say customer 1, 2, and 3 in order. The first one might purchase A or B. The second one might purchase A or B. The third one may purchase A or B. So if we try to make a sample space for purchasing of smartphones by these 3 customers, then we can talk about, for example, A, the first one takes apricot, the second one purchases B, and the third one purchases A. So we can think about all the variations of these letters, these fonts. Okay. And one more example that we'll be dealing frequently in this course is IC, integrated circuit manufacturing process. IC circuits, when they're manufactured, they are tested whether they work or not, or they meet the quality objectives or not. So the result of this testing, okay, let's say testing, yeah. Here is the manufactured ICE testing, and the result is either accepted, A, or rejected, R. Okay, there's no other option. Then if we model this experiment, we can say a sample space of A and R. So if we randomly take an IC from this flow, this process, we test it and get A or R, accepted or not accepted. This is how we model, you see, how we use models in experimentation, in experiments. The next example, again, we'll be dealing with in this course frequently, 6-sided die. A typical die, you know, that we may use in backgammon or other games. Observe the number of dots on the side facing upwards. So we just draw the, roll the die and look at the number of dots on the upside. Okay. And as you know, since this is 6-sided die, then the results will be 1, 2, 3, 4, 5, and 6. Okay, we have 6 different outcomes here. And then the sample space of this experiment will be 1, 2, 3, 4, 5, and 6. So if we roll a die, then we might get n of these numbers. Now we can define an event. Let's say event E1, roll 4 or higher. 4 or higher. So 4 or higher means that this one, and this one. So this event will be set the event where we have 3 numbers, 4, 5, and 6. Another event, E2, might be the roll is even. So we look at the even numbers in here. You see even numbers 2, 4, and 6. So the outcomes of this event will be 2, 4, and 6. Roll is the square of an integer. So we look at the numbers here, which are square of an integer. So 1 is square of 1. So that's one of the outcome. Next, 4 is square of 2. So that's another outcome. Then we can form the event as 2 consisting of 2 samples, 1 and 4. Do you have any question? Any question? I assume you are following. Okay, here is, again, we have 2 examples and 1 quiz here. And I'm sure that you can study these examples and then understand these examples and use them to solve this quiz. Okay? It's not so difficult. If you have followed the previous examples, then these two are quite easy to solve. Okay, next, probability axioms. Okay, there are three axioms of probability for any event. First of all, we use P bracket dot to represent probability measure, okay? And for any event A, probability is greater than or equal to 0, okay? Sorry, let me. So probability of A is greater than or equal to 0. So the minimum of probability measure is 0. Next, probability of S, here S is sample space, is unity, 1. And probability of mutually exclusive events from A1 to, let's say, AN, the union of these events, probability of union of these events is sum of the probabilities of each event. Okay? For example, if I have A1 and A2 mutually exclusive events, then probability of A1 union A2 is probability of A1 plus probability of A2. So, since these two events are mutually exclusive, then the intersection of these events will be 0. This is simply theorem 1-1. Okay? If we have M events from A1 and AM, the union of M events gives you A, and if any two of these events are disjoint, okay, then probability of A will be summation of these probabilities simply. Okay? How about theorem 1-3? Probability measure satisfies these relationships. Probability of empty set simply 0. Probability of A complement is equal to 1 minus probability of A. And for any two events, they are not necessarily to be mutually exclusive. The probability of union of these events will be probability of A plus probability of B minus probability of intersection of the two events. If event B is a subset of event A, then probability of A is less than or equal to probability of B. Okay? And the theorem 1-4, if we have an event B consisting of M outcomes, and probability of B will be summation of the probabilities of each outcomes. Next and final theorem. For any experiment with sample space S, where we have n outcomes, each outcome is equally likely. If each outcome is equally likely, then probability of any outcome will be 1 over n, the number of outcomes in the sample space. These are called equally likely events or outcomes. Next, conditional probability. Before that, this is important. In the textbook and in other books, you may see different notations. This notation, A intersection B, and probability of A intersection B is also given as probability of A comma B or probability of AB, so multiplication. So be careful. This might be used in this textbook or in other textbooks. Okay, conditional probability is a modified probability model that reflects partial information about the outcome of an experiment. And we usually use two events, A and B, in conditional probability. So one of these events, let's say A, is dependent on the result of B. Okay, and this is how we read it. Probability of A given B. So what is the probability of A given that B? Simply, if I know the probability of B, then I can talk about probability of A. So probability of A, condition it on probability of B actually. Now, probability of A given B can be written as probability of AB divided by probability of B. So this could be also written as probability of A intersection B divided by probability of B, or probability of A comma B divided by probability of B. Okay, so this is important. And theorem 1.6 for conditional probability, again, we have three axioms, actually similar axioms that we have seen in previous slide. Probability of A given B is equal or greater than 0, and probability of B given B is unity. And if I have an event as a union of some events, and if those events are disjoint, then probability of A given B can be written as probability of A1 given B plus probability of A2 given B plus so on. Okay, so here is an example. We have the same experiment in example 1.7, where we roll a six-sided die and all faces are equally likely. So the sample space here is 1, 2, 3, 4, 5, and 6. So probability, since these are equally likely, then probability of, let's say, 1 is equal to probability of 2, probability of 6. All are equal. Okay. Now, what is the probability of roll 4 or higher? Roll 4 or higher. So simply probability of this subset or event. It's going to be apparently, since this is 1/6, then it's going to be 3 divided by 6. Okay, so probability of, let's say, roll 4 or higher will be probability of 4, 5, 6, which is 3 divided by 6, so which is 1/2. So we count the number of outcomes in here and divide the total number of outcomes in the sample space. Roll an even number. So we here, for even numbers, we have 2, 4, and 6. So again, 3. So 3 divided by 6 is 1/2. roll the square of an integer. So square of integer. So this event refers to two outcomes, 1 and 4. So it's going to be 2 divided by 6, which is 1/3. Okay. Next example is about IC testing again. IC testing. We have two integrated circuits that come from the same silicon wafer, and observing in each case whether a chip is accepted or rejected. Okay? We have a wafer here, and there are two ICs. Okay, IC1 and IC2, and I test this whether accepted or rejected. Check this, test it, A or R, rejected. So altogether, if I look at here, the first one could be accepted, second one could be accepted, the first one could be rejected, the second one could be rejected. Sorry. Let me write again. So the first one is accepted, accepted, rejected, rejected, accepted, rejected, and rejected, accepted. So there are 4 different cases here, and we can define different events here. Okay. For example, let's say an event B, which is the first chip is the first chip is rejected. So let's see here which outcomes here we have. So first chip is rejected. So this one and this one. So then the result here, B could be RR or RA, 2 outcomes. We can define another event. The second chip is failure. Let's say BA. So A. The second chip is a failure. So I should take the outcomes with the second chip is R. Okay. So what are they? Again, this one and this one. So RR and AR. Okay. So we can construct such events from this example. Now, here how we use conditional probability based on this example. Okay, don't forget this example. We have a wafer, we have testing of ICs, and then there are accepted and rejected cases. Now, let's see here. We have a priori probability model. There rejected, probability of rejected is given, rejected, accepted is given, accepted, rejected is given, and accepted is given. So I know probability of each outcome. Find the probability of A, second chip rejected, and B, first chip rejected. Also find the probability, conditional probability that the second chip is a reject, given that the first chip is a reject. Okay? Second chip is a reject. So second chip a reject. So this is A. Given that the first chip is a reject. So this is B. So this simply asks probability of A given B. Okay. First of all, we have to calculate probability of A. Probability of A, the second chip is rejected.
Ben
So
anlamadım da tekrar anlatabilir misiniz bu kısmı?
Pardon?
Ben anlayamadım da bu kısmı tekrar anlatabilir misiniz?
1-12 mi?
Evet.
Okay.
Yani şu also find the conditional probability'den sonra anlayamadım.
Okay, I see. Now forget about this section and let's continue the first part firstly, and then I will describe the second also section, okay? Okay, first of all, we have again IC testing. And here I got two IC1, IC2. This is A and B. This is A and B. So the sample space, we construct the sample space. It's going to be A, R, and R. So is it clear? Next, I know the probabilities of each, yeah, and A is the second chip rejected. Second chip rejected, I look at here and identify those with second chip rejected. So this one and this one. So I just write here AR and RR. Is that clear? Now probability of A will be 1, 2, so 2 divided by 1, 2, 3, 4, 4. Okay? If it is equilikely, then that's going to be 2 over 6. Okay, for equilikely case. Sorry. I'm sorry. Again, for equilikely case, this is going to be 1 over 2. But here, the probability model here is given. So they are not equal, as you see. Then, instead of this equilikely case, so instead of this, I'm sorry, what happened? Okay. Instead of this, now probability of A will be probability of each outcome. So probability of AR plus probability of RR. AR here 0.01 plus RR 0.01, which is 0.02. So that's probability of A. Next, probability of B, that's very similar. Here, the B first chip is rejected. So the first chip is rejected, could be this one and this one again. So that gives you 0.02. Now the second part, that's more important. The conditional probability that the second chip is a reject. Okay? Given that the first chip is a reject. Okay? This means that I have to write probability of, let's say, the first chip is a reject. First chip is a reject is RA and RR. Condition, okay, given that the first chip is a reject. Sorry, the second chip is right here. Let me correct it. This should be second chip. I'm sorry. Second chip reject. So this one and this one. So AR and RR. Given that the first chip is a reject. So I just write the first chip is reject. RA and RR. Okay. Find this probability. This is equal to A actually, and this is equal to B. So this is equal to probability of A given B. And from the formula, I know that this is equal to probability of AB divided by probability of B. Okay? Probability of AB. What is probability of AB? Probability of AB corresponds to, if I look at the AB here together, what is it?
Both rejected.
Yeah, intersection of both, right? What is the intersection of this one and this one? Is RR, right? RR. So that's probability of RR, which is from here,
Yes.
0.01. Okay, just insert this into here, 0.01 divided by probability of B. Probability of B is 0.02. So the result is 1/2. Is that clear?
Yes, teacher. Thank you.
Okay, good. This is an example. Again, it's very similar to the previous one, actually. The experiment is different. Roll 2 fair-sided dice. I will skip this example, actually. This is very similar to the previous one, and we do not have enough time to give all examples, to study all examples. Partitions and law of probability. For a partition B, here we can talk about on this example here. Okay, we have a sample space here. Okay, and the sample space is split up into B4 sub-experiments, outcomes or events, B1 to B4, and collection of this all together forms the sample space. Okay, and we define an event A in sample space and divide this into 4 events, C1 to C4, and then this C1 to C4 union of them gives you A. And note that B1 to B4 and C1 to C4 all are mutually exclusive, right? Disjoint. Okay, B1 to B4 disjoint, and C1 to C4 disjoint. Okay, simply a partition refers to events that forms the sample space. So we have several theorems in here. For A, that is union of C1 to C4, and for any event A, here again with B, probability of A will be A intersection B. So we can simply draw A here, for example, like this, and intersection of A and B1. Okay, let us show it. Intersection of A and B1 will be here, right? Intersection of A and B2 will be here. Intersection of A and B3 in here, and A and B4 in here. So sum of this will give you A. And law of total probability, we have partitions B1 to B4, okay, as we said earlier. So here is the partitions. And the probability of BI is greater than 0 for all i's, and probability of A will be, so using this actually, probability of A will be summation of probability of A given BI times probability of BI. Okay, remember that probability of A BI, right, is going to be probability of A given BI times probability of BI. Okay, and finally, Bayes' theorem. Bayes' theorem relates any 2 events, A and B. Probability of B given A can be written in terms of probability of A given B, if we know probability of B and probability of A. These are usually called a priori probabilities, and this is called a posteriori probability. Here we have many examples. and these are quite easy. You can, I believe that you can do them by yourself. I will go to the last subject, independence. This is an important subject. Two events are independent if observing one event does not change the probability of observing the other event. Okay? Let's say if we have two events, independent events, A and B, then probability of AB will be probability of A times probability of B. Okay? Similarly, from here, probability of A given B will be probability of A because A is not dependent on B. Okay? Probability of B given A will be probability of B. Okay? So here, be careful. Independent and mutually exclusive events are not synonyms. Okay? Independent and mutually exclusive are different things. Independent is dependent on probability values in here, while mutually exclusive is simply disjoint events. Okay? Now, in order to check the independency of more than two events, okay, more than two independent events, we have to check every two or three of events, whether they are independent, mutually independent or not. So here there is a concept, mutually independent events, where we check, for example, if we have three events, we check A1 and A2. So we look at probability of A1, A2. This should be probability of A1 times probability of A2. So we check A2, A3, A1, A3, and finally A1, A2, and A3 altogether. If all conditions met, then we call that A1, A2, and A3 are mutually independent events. If there are more than three events, then we have to do this for all the variations of the events. Okay, here is an example. We have purchasing decisions again, the Phone Smart company, you remember. Okay. Three purchase decisions. Okay, each outcome, sequence of three decisions. Here we how to call it, B, let's go to 1.9, sorry, first. Okay, I'm sorry, 1.9. Let's go to 1.9. Okay, here we go. Three customers, Phone Smart store, the same experiment. We have buying or not buying. Okay, so we have a customer entering to the store. We have buying or non-buying. Okay, then we can look at three customers, for example. If all of them purchased a phone, then it's going to be buy. The first purchased one, the second not buying. B, B, N, for example, N, so three did not buy anything. So let's consider the experiment. This one. So remember this experiment. Are the events B2 that the second customer purchases a phone, and N2 that the second customer does not purchase a phone independent. Simply, BI corresponds to ith customer purchase. Okay, and N2 or NI corresponds to ith customer not purchasing. Okay, so we can list this simply. For example, B and N, B and B, BBN. So here, the first customer purchased. Here, the first and third customer purchased, and here I is 1 and 2. Okay, first and second customers purchased something. Now, here the question is, are the events B1 and B2 independent? Okay, in order to check whether they're independent or not, we have to look at B1 intersection B2, or probability of B1, B2, whether it's equal to probability of B1 times probability of B2. Okay? Now let's look at B1 and B2. The sample space here, easy. We start with B, 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 and B, B, N, B, N, B. All the variations of this goes to N, N, N. So total of 8 outcomes. Okay, here is the outcomes. And since they are equally likely, so probability of B, B, B is 1 over 8. Probability of N, B, N, 1 over 8. All I have similar or the same probability. Now, B2. The outcomes of B2. So here is B2, 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 B2. So the number of outcomes here is 4. So probability of B2 is actually 4 over 8. So how about N2? So the second customer did not purchase anything. So second customer should be N. You see. So probability of this is probability of B2. Probability of N2 is what? Again, 4 over 8. Let's see probability of B1. Probability of B1. For probability of B1, we use the outcomes here, B and N, B and B, and B, B, N, and B, B, B. The first customer purchased something. So probability of B1 is again 4 over 8. Now, probability of B1, B2. What is the probability of B1, B2? In order to find this, we have to determine first B1, B2, intersection of B1 and B2. So we look at intersection of B1 and B2. You see how many of these are the same. Let's identify them. This one is common, right? Here. What else? First and second should be the same. BNN, BNB, and BBN. So this one. This one. So this should be BBN and BBB. So probability of B1, B2 should be 2 over 8. So how about this probability of B1? We have already calculated that, right? Where is it? This one. So 4 over 8 times probability of B2, here it is, which is 4 over 8, So, are they equal? Okay, let's check. 2 over 8, 4 over 8 times 4 over 8. Okay, are they equal? No. Are they equal? Do you have any question? Okay, are they equal? They are equal. So we say that B1 and B2 are independent. Okay, I think that's enough. There is one more example. You can study these examples. You can study these examples, and if you have any question, then we can do office hour or discussion hour. You can ask your questions. Is there any question? General, I think you got some questions regarding with the course.
I have no